Hi everyone, myself Sonia Geo, a faculty at Silver Hills Public School. Welcome to the second part of the section, chapter Light, Reflection and Refraction. Things are not what they appear to be, they are different. Sometimes our eyes may be mistaken. Our eyes depend on the light that falls on them. So, the way we see things depend upon how light falls. Let us recall some day-to-day observations. A pencil immersed in water appears to be bent at the interface of air and water. A lemon kept in water in a glass when viewed from the sides appears to be bigger than its actual size. A coin in a glass tumbler filled with water appears to be raised when seen from above the water. The last one, tingling effect of stars. Yes, you got the point. It's due to refraction of light. So today's section I am going to discuss about the topic refraction of light. Refraction of light, the phenomenon of bending of light when it travels from one medium to another is called refraction of light. Do you know what is the actual cause of refraction? The basic cause of refraction is the change in the speed of light in going from one medium to the other. Light travels faster in air and light travels slower in water. Consider these two figures. In first figure, we can see that a ray of light travels from air to glass. Here, this air is a rarer medium. Rarer medium means light moves faster. In rarer medium, light moves faster. So, a ray of light travels from air to glass. This is refracted ray. This refracted ray bends towards the normal because glass is a denser medium and air is a rarer medium. Consider the second example. If a ray of light travels from glass to air, you know that glass is a denser medium and air is a rarer medium. Rarer medium means light moves faster in rarer medium. When a ray of light travels from glass to air, the refracted ray bends away from the normal. Refraction of light. Consider there are two media, medium 1 and medium 2. Consider our first medium is air and second medium is water. So, you know that air is a rarer medium and water is a denser medium. A ray of light incident. So, this black line represents interface which separates medium 1 and medium 2. This light bends towards the normal. So, we can say that this ray is the incident ray and the second ray is the refracted ray. Draw normal. You can see two angles, angle of incidence and angle of refraction. Angle of incidence means angle between normal and incident ray. Angle of refraction means angle between normal and refracted ray. Laws of refraction. The first law is incident ray, normal and refracted ray all lie in the same plane. Second law. The second law is also known as Snell's law of refraction. According to Snell's law of refraction, the ratio of sine of angle of incidence to the sine of angle of refraction is a constant, or we can say that sine I divided by sine R is a constant. This law is also known as Snell's law of refraction. There are two laws. First one, incident ray, refracted ray and the normal all lie in the same plane. Second one, the ratio of sine of angle of incidence to the sine of angle of refraction is a constant. Refraction of light through a rectangular glass slab. This is the rectangular glass slab made of glass. And the second figure shows the refraction of light through a rectangular glass slab. Glass slab experiment. Fix an A4 sheet paper on the drawing board using pins. Place a rectangular glass slab over the sheet in the middle. Draw normal. From the normal, draw one ray, the straight line. Take two pins, fix the two pins on this line. That means at A and B, fix two pins. Try to locate the image of these two pins through the edge SR. So from this side, try to locate the position of the images. Note down the point C and D. At C and D, fix another two pins. Make sure that these four pins should be in a straight line. After that, remove the slab, remove all pins. Join the line EF and FD. We can say that this ray AE is called incident ray. The ray EF is called refracted ray and the ray FD is called emergent ray. And you can see that there are two refractions take place. One is from air to glass and second refraction is from glass to air. This angle of incidence. Angle of incidence means angle between normal and incident ray. This angle is known as angle of refraction. Angle of refraction means angle between normal and refracted ray. Then see angle of emergence. Angle of emergence means angle between emergent ray and normal. When you are extending incident ray, you can see that the extended incident ray and this emergent ray will be parallel to each other because here this angle of incidence is equal to angle of emergence. So this extended incident ray and this emergent ray parallel to each other. Refractive index. This is a measure of how much light slows down when it goes into a new medium. And you know this equation N is equal to C by V, where N is known as refractive index. C means speed of light in air and V means speed of light in medium. For example, the refractive index of water is 1.33. So we can say that N suffix W, NW. NW is refractive index of water. NW is equal to 1.33. What is the meaning of that? We can say that the ratio of speed of light in air or vacuum to the speed of light in water is 1.33. Refractive index means it is a measure of how much light slows down when it goes into a new medium. For refractive index, there is no unit because you know numerator side and denominator side, this is speed of light in air or vacuum divided by speed of light in medium. Therefore, there is no unit for refractive index. Consider a beam of light travelling from medium 1 into medium 2. Our first medium is air and second medium is glass. Let V1 be the speed of light in air and V2 be the speed of light in glass. We can write one relation N21. N21 means refractive index of second medium with respect to first. That means refractive index of glass with respect to air. N21 is equal to V1 divided by V2, where V1 is the speed of light in first medium and V2 be the speed of light in second medium. Similarly, we can define N12. N12 means refractive index of first medium with respect to second. N12 is equal to V2 divided by V1, where V2 is the speed of light in second medium and V1 is the speed of light in first medium. I repeat, N21 equals V1 divided by V2, N12 equals V2 divided by V1. Absolute refractive index. Absolute refractive index N is equal to C divided by V, where C is the speed of light in vacuum and V is the speed of light in medium. Next topic, image formation in lenses using ray diagrams. These are lenses, spherical lenses. Spherical lens is a piece of a transparent refracting material which is bound by two surfaces. There are two types of spherical lenses, convex lens and concave lens. First one is convex lens. Convex lens is also known as converging lens. After refraction, all the refracted rays meet at one point. Concave lens is known as diverging lens. See, you can see that all the refracted rays diverge from the point, and if you are extending all these refracted rays, it will meet at focus point. Some terms associated with spherical lenses. First one, aperture. The aperture of a lens is the diameter of the circular edge of the lens. This is the diameter. See, we have to consider the refracting plane of the lens, and the diameter of the circular edge of the lens is called aperture of the lens. This is concave lens. Representation of concave lens is this like, concave lens is a diverging lens. The diameter of the circular edge of the lens is called aperture of the lens. Second one, center of curvature. This is the refracting surface of the lens. For concave lens, this is the refracting surface. Actually, you know that if we are drawing, we will get two spheres. Both convex and concave, we will get two spheres. Then both these spheres have centers C1 and C2. The centers of these spheres are called centers of curvature of the lens. For concave lens also, we can see that there is C1 and C2. So, center of curvature means the centers of these spheres are called centers of curvature of the lens. Principal axis, an imaginary straight line passing through centers of curvature of the two surfaces of the lens. Here also this imaginary line passing through the centers of curvature, this line is known as principal axis. Fourth one, optical center. Optical center of a lens is a point on the principal axis such that a ray of light passing through it goes undeviated. You can see that for the case of concave lens and for convex lens. Any ray passing through optic center without any deviation, that ray refracts. So, this point is called optic center of the concave and convex lens. The uses of convex lens, first one used in hand lens, used in microscope, used in camera. Uses of concave lens. Concave lens used in telescope, binoculars, etc. Next topic, rules for image formation in lenses. First rule, ray of light from the object parallel and close to the principal axis after refraction from the lens passes through the point focus. This is concave lens. You can see that a ray of light incident on this concave lens. That light refracts. If we are extending that refracted ray, it will meet at F. This is the first rule. Second rule, a ray of light from the object passing through the focus of a lens parallel to the principal axis after refracting through the lens. For the case of concave lens, any ray which is passing through the focus, that refracted ray will parallel with the principal axis. The last rule, a ray of light from the object passing through the optical center of a lens goes straight after refracting through the lens. Consider convex lens and concave lens. Any ray which is passing through the optic center, that ray refracts without any deviation. Along its same line, that ray refracts. So, we have studied about all the rules. Now, we are going to study about the ray diagrams of lenses. First one, convex lens, image formation by convex lens. Consider the position of the object is at infinity. From infinity, some of the parallel rays incident on this convex lens. All these light rays refracted. You can see that all these are parallel rays. So, parallel rays refracted through point F2, focus point F2. All the refracted rays meet at the point F2. So, where is the image formed? The image will be formed at F2. You can see that what about the size of the image? It is very small. We can say it is point sized image. The nature of the image is real and inverted. Second case, the position of the object is beyond C1. Here you can see F1 and 2F1. Actually this 2F1 is C1, center of curvature C1. You want to keep the object beyond 2F1. So, this BA is the position of the object. From the point A, a ray of light incident parallel to the principal axis. That refracted ray will pass through the point F2. Another ray of light passing through the optic center. Through its same line, that ray refracts. Then you can see that both these refracted rays meet at A dash. From the point A dash, draw a perpendicular line to the principal axis. Here A dash, B dash represent the position of the image. Where is the position of the image? Between F2 and 2F2. And what about the size of the image? This is object size and this one image size. So, we can say that image size is diminished and nature of the image is real and inverted. Third case, position of the object is at C1. C1 or 2F1. Consider BA represent the position of the object. From the point A parallel ray to the principal axis incident on the convex lens, the refracted ray will pass through another ray of light which is passing through the point optic center. Along its same line that ray refract. Both these refracted rays would meet at A dash. From the point A dash, draw a perpendicular line to the principal axis. A dash B dash is the image. Then what about the size of the image? You can see the difference. We can say the size of the object and size of the image remain same. And what about the nature of the image? The nature of the image is real and inverted. Position of the image is at C2. If we are keeping object at C1, we will get image at C2 and the image size and object size remain same. Fourth case, position of the object between F1 and 2F1. This is F1 and this one 2F1. Place object in between F1 and 2F1. From the point A ray incident on this convex lens. That ray will pass through the point F2. Another ray of light is passing through the point optic center. Both these refracted rays meet at A dash. A dash B dash represents the position of the image. Where is the position of the image? Beyond 2F2. And what about the size? The size is enlarged. Fifth case, position of the object is at F1. This is F1, this is 2F1. Keep your object at F1. From the point A ray of light incident and that ray will pass through the point F2. Another ray of light which is passed through the point optic center. Both these refracted rays would meet at infinity. So what about the nature of the image? The nature of the image is real and inverted. The size of the image is enlarged. Position of the image is at infinity. Sixth case, position of the object between F1 and optic center. Consider BA is the position of the object. From the point A ray of light incident parallel to the principal axis. That ray passes through the point F2. Another ray of light passes through the point optic center. Then extend both these refracted rays. You can see that this side, left side of the lens, both these refracted rays will meet at the point A dash. So the image is A dash B dash. This is the case of the virtual image of convex lens. For getting virtual image, we want to keep our object in between F1 and optic center. That image size is enlarged. Nature of the image is virtual and erect. Position of the image is in front. So these are the cases which we have discussed. You know that only one case for getting virtual image, we want to keep our object between F1 and optic center. All other cases are real and inverted images. Next one, image formation by concave lens. This is concave lens. You know concave lens is a diverging lens. So virtual and erect image is formed. Only two cases. First case, the position of the object is at infinity. From infinity, two parallel rays incident on this concave lens. These two rays refracts. If we are extending these two refract rays, it will appear to meet at F1. So where is the position of the image? The position of the image is at F1. The size of the image is very small. We can say it is point sized. and the nature of the image is virtual and erect image. Second one, position of the object between F1 and 2F1. Consider BA is the object. From the point A ray of light incident on this concave lens and that ray refracts another ray of light which is passing through the optic center. If we are extending both these refracted rays, that will meet at A dash. Draw a perpendicular line to the principal axis. This A dash B dash is the image, and you know the size of the image is small. The position of the image is between F1 and optic center, and the nature of the image is virtual and erect. Next one, sign convention for spherical lenses. First one is convex lens, second one is concave lens. From this optic center, the things in the left side taken as negative and the distances in the right side taken as positive. That means the distance from O to F1, that is the focal length of the lens, right? And the distance from O to F1, that is the radius of the lens. The distances from O to F1 and then from O2 to F1 taken as negative. But suppose if the image is formed at the right side of the lens, then we can say the distance from O to F2 or the distance from O2 to F2, all these distances are positive. For the case of concave lens, the same rule is used. The things in the left side taken as negative and the distances in the right side taken as positive. Then about the upward height and downward height. The upward height is taken as positive, downward height is taken as negative. The same thing is for concave lens also. We are keeping the object always in front of the lens and that is in upward direction. Then for the case of inverted image, that in height is negative. Sign convention for thin lenses. Image location position positive when image is in back of the lens, negative when the image is in front of the lens. Then image height positive when image is upright, negative when image is inverted. R1 and R2 radius of curvature. Positive when center of curvature is in back of the lens, negative when center of curvature is in front of the lens. Focal length of convex lens is positive and focal length of concave lens is negative, because convex lens is a converging lens and concave lens is a diverging lens. Lens formula. The lens formula is 1 by V minus 1 by U equals 1 by F. Lens formula means it is the relation between object distance, image distance and focal length. That relation is 1 by V minus 1 by U equals 1 by F, where U is the object distance, V is the image distance and F is the focal length. Next one, magnification. Magnification is the ratio of height of the image to the height of the object, means M equals height of the image divided by height of the object. M is equal to H dash divided by H, where H dash is the height of the image and H is the height of the object. Or in another way, we can say in terms of image distance and object distance. Magnification M is equal to V divided by U, where V is the image distance and U is the object distance. Power of a lens. It is the ability of a lens to converge or diverge the ray of light falling on it. The power of a lens is defined as the reciprocal of focal length of the lens. The letter P is used for the power. Then power P is equal to 1 by F. What is F? F is the focal length of the lens. The power P of a lens or focal length F is given by P is equal to 1 by F. The SI unit of power of a lens is diopter, denoted by the letter capital D. 1 diopter is the power of a lens whose focal length is 1 meter. We can define 1 diopter. 1 diopter is the power of a lens whose focal length is 1 meter. We can say that 1 diopter equals 1 meter raised to minus 1. There are some questions based on power of a lens. First question, find the focal length of a lens of power minus 2 diopter. Power is given, power P equals minus 2 diopter. What type of lens is this? See, power is given, the power is minus 2 diopter. If the power is negative means that lens is concave lens. So, the second part, what type of lens is this? This lens is a concave lens because power is minus. Power is minus 2 diopter. Then we want to find out the focal length of a lens. Power P equals minus 2 diopter. Then focal length F. We know one equation. P is equal to 1 by F. Then we can say that F is equal to 1 by P. That is 1 divided by power is minus 2. 1 divided by minus 2. 1 by 2 is 0.5. This minus symbol. So, minus 0.5. The unit is meter. This is our answer. The power of a lens is given, then we can find out focal length by using the equation F is equal to 1 by P. The answer is minus 0.5 meter and this lens is concave lens because focal length is negative. You have studied that the focal length of concave lens is negative. Second problem. A doctor has prescribed a corrective lens of power plus 1.5 diopter. What is the power? P equals plus 1.5 diopter. Find the focal length of the lens. Is the prescribed lens diverging or converging? Power is given plus 1.5 diopter. If the power of a lens is positive, then that lens is convex lens. So, what type of lens is this one? This is converging lens. Convex lens is the converging lens. Then we can find out focal length. We know the equation P equal to 1 by F or F is equal to 1 by P. The focal length is given by 1 by P. That means 1 divided by plus 1.5. How to do this calculation? Both sides multiplying by 10. 10 divided by 15. Then divide. 10 divided by 15. 0.6 times. So, 0.66. The answer is plus 0.66 meter. Then for the question, if the focal length is in terms of centimeter, you should convert that into meter. Then only you can write the unit diopter. Okay. Third question, find the position nature and size of the image formed by a convex lens of focal length 20 centimeter of an object 4 centimeter height placed at a distance of 30 centimeter from it. First of all, read your question 2 or 3 times. Then write down all the things given in the question. It is a convex lens. So, you know convex lens, the focal length of convex lens is positive. So, we can write f is equal to focal length of the convex lens is positive, f is equal to plus 20 centimeter. An object 4 centimeter height, that means height of the object h equals 4 centimeter. Height of the object is in upward direction, so the symbol is plus. Distance of 30 centimeter. You know that the distance is always in front of the lens. So, we can write u is equal to minus. The object distance is always negative. U is equal to minus 30 centimeter. We know focal length and object distance. We can find out image distance. The equation lens formula is 1 by V minus 1 by U equals 1 by F. To find V, 1 by V equals 1 by F plus 1 by U. Substitute all the values in the equation. 1 by V equals 1 divided by focal length is 20, 1 by 20 plus object distance is minus 30, 1 divided by minus 30. 1 by V equals 1 by 20 minus 1 by 30. We can write 1 by V equals LCM 60, 20 into 3 is 60, so 1 into 3, 3 minus 30 into 2 is 60, so 1 into 2, 2. 1 by V equals 3 minus 2 divided by 60, that is 1 by 60. So, V is equal to 60 centimeter. Then second part, find the position, nature and size. So, we have to find out magnification and height of the image. For that, consider the equation magnification m equals h dash divided by h, that is equal to V by U. And we know the values V equal to 60 centimeter. Height of the object is given, height of the object is 4 centimeter. Then U is also given, U is equal to minus 30 centimeter. Substitute all these in this equation, we can write magnification m equals h dash divided by h 4 centimeter equals V by U. V is 60 centimeter. 60 divided by U, U is minus 30. Cross multiplying, we can write 60 into 4 equals h dash into minus 30. 60 into 4 equals h dash into minus 30. We can write minus 30 h dash is minus 30 h dash equals 60 into 4. Therefore, h dash is 60 into 4 divided by minus 30. You know 60 by 30 is 2, minus 2 into 4 minus 8. The height of the image is minus 8 centimeter. And for magnification, m equals h dash divided by h, we can write minus 8 divided by height of the object is 4. Therefore, magnification is minus 2. So, this image is real and inverted image. Image distance is 60 centimeter, height of the image is minus 8 centimeter and the magnification is minus 2. If the magnification is minus 2 means that image is real and inverted image. That's all. Thank you.